So, in the last few videos we have seen how to find the two linearly independent solutions for second order homogeneous equation with variable coefficients by the Frobenius method when x equal to 0 is a regular singular point. So, when 0 is the only regular singular point and there is no other singular point, when you have x greater than or equal to 0 or like less than or equal to 0, the solution will be valid. So, y1x and y2x, when you calculate it as a Frobenius series, the series is absolutely and uniformly convergent on any closed interval in x positive or x negative. Okay, that is what we have seen. We have seen all the three cases when the initial equation roots, when the difference is integer, when the roots of the initial equation difference is integer, which is non-zero, and if it is they are equal roots, so the difference is 0 and the difference is non-integer. Okay, so all the three cases we have demonstrated with the example. With an example that we have shown that find the general solution of second order homogeneous equation with variable coefficients. So, we will apply this technique, Frobenius method, to find the general solution of an important equation in physical sciences. It is called Bessel equation, for which 0 is a regular singular point and there is no other singular point in it. Okay. So, we will consider such equation, the Bessel equation, in this video. So, we will try to see it has a parameter, some alpha. So, the parameter depending on the parameter you will be falling in one of those cases in the method. So, either when you calculate the initial equation, so initial equation when you calculate the roots, the root difference will be depending on this parameter. So, depending on this parameter values, so the difference between these initial roots is either 0 or a non-zero integer or non-zero non-integer. Okay. So, we will see all the three cases. So, we will start with this Bessel equation. Bessel equation. We will try to find the general solution of this equation. So, the equation looks like this. You have x square y double dash plus x y dash plus x square minus alpha square. Alpha is the parameter, y equal to 0. So, where is this valid? You see that 0 is x square, a naught of x is x square. So, it is 0 at x equal to 0. So, 0 is the singular point and there is no other singular point. So, it is x greater than 0 or x negative, x less than 0. So, these are the two domains. Each of the domain you can consider the equation. So, we will do only for x positive. So, x negative, when you do whatever the equation, whatever the solution you find when x is negative, wherever x is there you just put mod x. Wherever log x comes in the second solution, you have to use log mod x. Okay. Or when you have the powers of rational real numbers, x power something k. Okay. K is satisfying is the root of the initial equation. So, in there, because you do not know what because x is negative real number power, you do not know the real power of negative number. So, you have to use positive, because the positive powers are defined. So, mod x power k so that is where you choose mod x. Instead of write x, you can write mod x, so that it is the case for x negative. So, mod x when x is less than 0 is going to be minus x, that is positive. Okay, minus x power of k. So, this is the equation. So, you see that 0 is a regular singular point. As usual, since the reason is a1 divided by a naught, that is 1 by x, x divided by x square is 1 by x into x, limit x goes to 0. This is 1, which is finite, and limit x goes to 0, a2 of x, that is x square minus alpha square by x square. So, this is also into x square. So, this into x square is also is actually minus alpha square. So, depending on the value you give alpha. So, alpha is given. So, alpha is a parameter. So, you can choose as a real number. Okay. So, alpha square is always positive because alpha is in a real number. So, alpha square of any real number is a positive number. So, you have a non-negative number you have. So, alpha square, alpha can be alpha square. So, without loss of generality you can choose alpha is always greater than or equal to 0. Okay. So, this is what? So, is a regular singular point. So, we will just because it is a regular singular point, if you want solutions in the for x greater than 0. So, you look for solutions by Frobenius series method, Frobenius series solution if you look for in this form x power k sigma n is from 0 to infinity Cn x power n for x positive and C0 without loss of generality we assume it is non-zero. So, this is how you have chosen as a solution. Now, you simply substitute into the equation, get all the unknowns k and Cn's. So, substitute. So, you have y dash of x which is sigma n is from 0 to infinity Cn x power n plus k into n plus k. So, n plus k comes out. So, you have minus 1 n plus k x power n plus k minus 1. This is 1 y double dash of x will be n is from 0 to infinity n plus k minus 1 into x power Cn. You have a Cn constant x power n plus k minus 2. So, this is these three substitute into the equation, given equation. So, we will have x square, since x square y double dash plus xy dash plus x square minus alpha square y equal to 0. Okay. So, this is the equation. So, you substitute all this y and y dash. So, you have x square y double dash will be n is from 0 to infinity n plus k minus 1 Cn x power n plus k. You have minus 2 and you multiply with x square, it is going to be x plus x power n plus k. Similarly, this will be from n is from 0 to infinity n plus k Cn x power n plus k. Minus 1 goes because you are multiplying with x plus x square y, you can write it like n is from 0 to infinity Cn x power n plus k plus 2. So, this as you see this, okay, and then we will change the index later. So, right now you write minus alpha square y. So, that is alpha square you write y Cn x power n plus k, which is equal to 0. So, you see that all the powers are x power n plus k in these three except this one. So, you change the index as usual. So, n is, if you replace n is n minus 2, then this x powers will become x power n plus k. So, n equal to n minus 2 make it n plus k. Okay. So, n equal to n minus 2, and then when you put n equal to n minus 2 is running from n is from 2 to infinity. So, this is what it equation. Now, all x powers are n plus k. So, what is the isolated terms? You write n equal to 0 and n equal to 1 you write separately, and all the series are running from 2 to infinity, that you can write together. So, this gives me n equal to 0, you have k into k minus 1 into C0 x power n x power k, okay, plus n equal to 0. So, you have k times C0 x power k, and then there is n equal to 0 here. So, I have minus alpha square C0 x power k. So, this is what you have for n equal to 0. N equal to 1, you have k plus 1 into n equal to 1. So, k into k plus 1 into C1. Okay. So, you can also take that C1 is always common here in these three series. So, you have C1, you can take it out, C1 times x power k plus 1. I use n equal to 1. So, this is what you have. The first series you have k into k plus 1, next series plus you have n equal to 1, you have k plus 1 and then minus alpha square, simply alpha square. This is what you have. So, plus now everything is running from 2 to infinity. So, you can combine together. So, you have n plus k. So, n plus k into n plus k minus 1 and here n plus k. So, you are adding them together. So, that will give n plus k square. So, n plus k is out common and you have n plus k minus 1 and there is a plus 1. So, that is going to be n plus k. So, you have together it is a square and you have here minus alpha square. So, this is what with Cn, and then and here simply you have Cn minus 2. Okay. So, this into x power n plus k, n is running from 2 to infinity. So, this is 0. So, this is what it becomes 0. So, you see that C naught is common. So, I can write it outside C0. So, I remove this C naught out here and x power k also common. So, I can take it out, x power k. So, you see this is a power series. So, you can equate because C0 not 0, that is the assumption, right. So, you have chosen that C0 is non-zero. So, this has to be 0, that means this has to be 0. This is the initial equation. So, x power coefficient, x power k coefficient is 0 will give me initial equation. K into k plus 1, k minus 1 plus k minus alpha square equal to 0. So, this is actually equal to k square minus alpha square equal to 0. So, this will give me k equal to plus or minus alpha, alpha and minus alpha. So, alpha, if you assume without loss of generality the alpha is positive greater than or equal to 0. So, this root k1 will be alpha. Okay. So, you can fix what is your bigger root, k is k1, okay, or k1. So, what is your k1 bigger root, call this alpha, and k2 is minus alpha if alpha is greater than or equal to 0. If alpha is negative less than or equal to 0, so you can choose k1 as minus alpha. Okay. Bigger root will be small, bigger root will be when alpha is negative, bigger root will be minus alpha. Okay. So, assume that alpha is always so you can say that without alpha is actually full R, but without loss of generality now we can choose that this is greater than or equal to 0. Okay. Assume that alpha is greater than or equal to 0. So, even if alpha is negative you can simply change the roles of k1 and k2. So, bigger root will be minus alpha if alpha is negative. So, you have a bigger root, this is the bigger root alpha and this is the smaller root, this one. So, what happens? So, because now what happens to the other part? So, now if you equate coefficient of x power k plus 1 C1 into k square k plus 1 square rather, okay, k plus 1 square minus alpha square, okay, into C1 has to be 0 if you equate x power k plus 1 coefficient. So, this implies because k is alpha or minus alpha, right. So, those are your roots, k equal to alpha or minus alpha. So, k plus 1 square will never be alpha square, okay, or k minus, so minus alpha plus 1 square or alpha plus 1 square can never be alpha square. So, this means this is non-zero. So, that means this cannot be 0. So, that means C1 has to be 0. So, this is what you found, what is the first coefficient C1. And now equate the general coefficient for n equal to 2, if this you make it 0. So, you get a recurrence relation which is equation coefficient of x power n plus k, n is from 2 to onwards 0. So, you have n plus k whole square minus alpha square into Cn plus Cn minus 2 equal to 0 for every n 2, 3 onwards. So, now you can put n equal to 2, so you get C2. So, you calculated C1, you find C2, C2 will be equal to minus C naught divided by 2 plus k plus 2 square minus alpha square. Okay. And then what is C3? What is C3? If I calculate C3 minus C1 divided by any C3 will be k plus 3 whole square minus alpha square. K value is either alpha or minus alpha, so this will never be 0, the denominator never be 0, but I know that C1 is 0, so that means 0. So you get C4 will be minus C2 divided by this one, so you have plus C0 divided by 4 plus k whole square minus alpha square, this is 1, and you already have for C2 C0 divided by this you have 2 plus k whole square minus alpha square. So this is what you have, and then C5, which is again minus C3 divided by denominator, which is k plus 5 whole square minus alpha square, which is non-zero, but you already know that C3 is 0, so this is 0. So like that you can go on. Okay. All the odd coefficients will be 0, all the even coefficients you can write generally, you can expect it's something like this, C2m, which is C0 divided by, and you can write, now you can fix it, it's a bigger root. If you fix your bigger root, okay, that where k is, so you can write it if you want. So k is actually, so if or you can simply write C0 divided by, so you have 2 plus k whole square, so you can fix it later also, minus alpha square, 4 plus k whole square minus alpha square up to, what is the next part? So you have 2m plus k whole square minus alpha square, this is what you get. So whenever you have even coefficients 2m, m is from 0, 1, 2 onwards, m is actually from 1 onwards, so 2 onwards. Okay. That means m is from 1, 2, 3 and so on, that means C2, C4 and so on. So C naught, you do not know, still arbitrary, so C naught you cannot calculate. So what you get is, if you only put m equal to, it's actually valid, it's only from m is equal to 1 to infinity. So if you put m equal to 0, so you have, that is like you have C0 by 0, so that is not defined. So m is from 1, so that is where you know C2, C4, so you have this, and all other C2m plus 1 will be 0. Okay. So you can write here, so if you want you can write C2m plus 1 is 0 for every m equal to 1, 2, 3 and so on. Okay. With C1 is 0, so that will not have 0, so m equal to 1 you get C3 onwards, C3 onwards you wrote. Okay. So C naught is arbitrary. So this is what you have in general. So I did not fix my k is actually either alpha or minus alpha. I know that whatever may be the case, whatever may be the value of alpha, always bigger root, when alpha is greater than or equal to 0, bigger root is always k1. So put k equal to k1, which is alpha, so you can get all your coefficients in terms of C naught. Okay. So let k equal to k1, which is alpha, which is positive. Okay. If you put this, what I get is C2m equal to C0 divided by k equal to alpha. So you have alpha plus 2. So what is the first term? Alpha plus 2 whole square minus alpha, alpha plus 2 whole square minus alpha square, that is actually alpha plus 2 minus alpha into alpha plus 2 plus alpha. So you have 2 alpha plus 2, here alpha goes 2, this is what you will get. Okay. So you get 2, similarly here 4 and then 6, 8 up to 2m. Okay. So this is what you get from first term, each of these if you expand like this, okay, so you have this if you write, so 2 next here you get 4, like that you get it here 2m. What is the other part? Other part will be 2 alpha plus 2, and here 4 plus alpha plus alpha, so 4 plus, so 2 alpha plus 4 up to 2 alpha plus 2m. This is what you have as your C0. So this implies I always have, for bigger root I always have a solution, that is the power series solution. Without I will not have a problem in the method of Frobenius. For the bigger root, so you will always get all the coefficients which I got, only I could get only even coefficients. So what is the solution? Y1 C0 into x power k, k is alpha. So you have x power alpha, x power k is alpha, and the series is C0 plus C1x plus C2x square. This is what if you expand. This is the series you looked for, right? So this is equal to x power alpha. C0 I could not find, C1 is 0, C2 is, what is C2? C2 is minus C0 by, so C is minus C0 by, what do you get? So if you do this or put k equal to alpha, so you have 2 into 2 alpha plus 2. So this is your x square, and next term will be C4. C4 when I do this is plus, okay. So now it will be plus, so you have C0 divided by 2 4, 2 alpha plus 2, and then 2 alpha plus 4 into x power 4. So because of that alternative positive and negative sign, you will see you have that this power m. So that I missed. So you have actually what you have is minus 1 power m. So you have minus here plus here, when m equal to 1 it's minus, m equal to 2 you have plus, and so on. So you can have the nth term, so you can write the even term, which is C0 minus 1 power m divided by whatever you have here, 4 2 4 6 up to 2m is 1, and 2 alpha plus 2, 2 alpha plus 4, 2 alpha plus 2m. So this is your nth term into, so you, once you have nth term you have x power 2m and so on. So this is what is your series solution. So this is actually equal to x power alpha C0, you can take it out and you can sum it up now. If you sum it up, so what do you have? M is running from, so if m is running from 1, you write it as it is. So you have 1, okay, and then plus sigma, this term I am not writing, I am not putting in the sum. So we have m is from 1 to infinity. So all from m is from 1 to infinity, I have my C2m, okay, m to m. So you can now simply see C0 you took it out, and what you have is minus 1 power m x power 2m divided by, so you can write this 2 power, so this will be 2 here, 2 here, okay. So what do you have? So 2 here up to 2 you remove. What is left is 2, I can write 2 into 1, 4 you can write 2 into 2, 6 I can write 2 into 3, and so on m. So these are the product of all these. So I have m 2n's, so you have 2 power m, and then and I have m factorial, okay. And what you have here is again you have 2 here, 2 take it out like that. What is left here? 2 into alpha plus 1, alpha plus 2 into alpha plus m. So that also if you add, you have 2 power m into alpha plus 1, alpha plus 2, and so up to alpha plus m. Okay. So, this is what you have. So, put it together 2 power m 2 times, you have 2 power 2 m. So, this is what is your series solution, first non-zero solution, okay, for the bigger root in the Frobenius method. Okay. Now, I have not chosen any, I have not fixed any alpha. So, alpha is a bigger root is always, when alpha is positive, bigger root is always alpha. So, I have this one series solution I will always get, that is your y1. Now, we will see the different cases. In different cases, so what happens? The simplest case 1, what is the initial roots? Roots are k1 minus k2, which is alpha minus alpha, that is 2 alpha. If 2 alpha is not an integer, then this is what is the case 1. Case 1 in the Frobenius method. In this case, actually even if you do for k equal to k2, okay. So, whatever you have done here, I put k equal to k1, I got the one solution. When the difference of the roots is non-integer, you see that when you put the other root, which is k equal to minus alpha, you get the same solution. So, you can get all the coefficients. What happens when I put instead of k, if I put k equal to minus alpha, wherever you have k, you have minus alpha. So, instead of alpha plus 2, you have minus alpha plus 2, minus alpha square. So, that become, so instead of, so you will get, you will only have to interchange. Okay. So, what happens, the product now, so minus alpha 2 plus 2 minus alpha, that is 2 minus 2 alpha, or minus 2 alpha plus 2. Okay. And then other one is minus alpha plus 2 plus alpha, you will get 2. So, only you will change you will interchange, instead of you are writing 2 into 2 alpha plus 2, you will get minus 2 alpha plus 2 into 2. Okay. So, this is whole thing will be as it is with alpha is minus alpha, and this will be as it is. Okay. So, you will get the same coefficients, but with alpha is minus alpha. Okay. So, that is what you will get if the difference is a non-integer. Non-integer, you should not have a problem, okay, because the denominator will never be 0 if the difference is non-integer. You see that I have got 2 alpha plus 2, right. The denominator I have minus 2 alpha plus 2 minus 2 alpha plus 4. Only if 2 alpha equal to 2, that is what is the problem. Okay. 2 alpha equal to 4, that is where the problem. But because 2 alpha is not an integer, so it will never be 2, 4 and so on. So, I do not have issue. So, you get simply by put k equal to k2, which is minus alpha, will give me into where? So, into the recurrence relations, into the recurrence relation RR, let me write it as RR, recurrence relation, to get C2Ms, okay, as it is. C2Ms, you get the same C2Ms with alpha replaced by minus alpha. That is what you will get. Okay, if you can check it. From this step onwards, you try to put k equal to minus alpha. You will see that this is what you will get. Instead of alpha, you have minus alpha. But you know that 2 alpha is not an integer. This denominator never be 0. So, I could get what is my C2Ms, and all the odd coefficients are anyway 0, because either you put alpha equal to minus alpha, does not matter. When k equal to minus alpha, still this is not 0. So, this because C1 is already we found 0, and you see that all the odd coefficients are 0. So, you have a second solution very easily as C0 x power minus alpha, and here 1 plus sigma m is from 1 to infinity minus 1 power m x power 2m divided by 2 power 2m m factorial. Here I have minus alpha plus 1, minus alpha plus 2 and so on, minus alpha plus m. This is what is the second solution. Okay. So, this is your first solution, this is your second solution in the case 1 when the difference between these two roots, that is 2 alpha, is not an integer case. Okay. So, we can write the general solution of Bessel equation. The Bessel equation is yx, if you can write yx, some arbitrary constant C1 times, okay, C1 times C0, you can take it as 1 here, okay, C0 you take it as 1, C0 you take it as 1, so that you have two non-zero solutions. So, C1 is an arbitrary constant, so you take with y1, and then C2 is another arbitrary constant, you take another linearly independent solution. So, this is your general solution of a Bessel equation if 2 alpha does not belongs to Z, non-zero integer, okay, does not belongs to. This is what is the case, okay. This as a straightforward case 1. And it is also, so from this you can see that this is x power alpha, alpha is positive. At 0 it is 0 is an ordinary, 0 is a singular point, but the solution as such it is defined even at x equal to 0, okay. Actually it is defined x positive, okay, as a solution, and as a function here this solution just like Legendre equation, Legendre function, Legendre solutions, Legendre polynomials, though they are solutions of a differential equation in the open interval -1 to 1, but those polynomials are defined everywhere. So, y1 of 0 is actually x power alpha, okay. So, you see that as a solution which is bounded, that is what you are saying. So, but here alpha is positive, x power minus alpha, when you put x equal to 0, so you have unbounded solution, okay. So, y2 is unbounded. So, this is a bounded solution at x equal to 0, unbounded solution. At x equal to 0, okay. In the neighborhood, so though in the unbounded are in the neighborhood of x positive, because it is not defined at x equal to 0, okay. When you closely very small values of x is always going to be big value, okay. So, it is unbounded in the neighborhood of 0. So, you can say that this is also in the as x very close to 0 is still bounded. So, okay, as a limit it exists, as limit x goes to 0, y1x is bounded, y2x limit x goes to 0 is unbounded. This is what we see as a simple case, what we learnt in the Frobenius method. When you apply the case 1, so you get the nicely two linearly independent solutions. So, take a linear combination of it, you get the general solution of the Bessel equation. And so, these bounded solutions, like in the Legendre equation, in the Bessel equation also, these bounded solutions y1 customarily by choosing this C0. So, you have this what we have chosen as C0 equal to 1, this is what is my y1 as a non-zero solution. But if I fix some conventionally some C0, so that this whole thing is simplified, okay, that is how I can define as a Bessel function, okay. So, I write what is the definition of Bessel function, Bessel function of first kind. So, you get a solution as a Frobenius first solution for the bigger root is always called first kind Bessel functions. Bessel functions of first kind, we call this J alpha of x. By choosing, you simply take C0 as some fixed number. So, conventionally we choose C0, if you choose 1 over 2 power alpha gamma function, this is a gamma function, we will see what exactly it is, gamma into alpha plus 1. So, this you choose into x power minus alpha, x power alpha. So, instead of C0 you choose, instead of 1 you choose this number, any constant multiple of y1 is also a solution. So, C0 if you choose like this, and then it will become x power alpha here. So, you have x power alpha and you have a sigma, n is from rather you have 1 plus sigma, m is from 1 to infinity minus 1 power m x power 2m. So, whatever you have, you write, so x power 2m divided by 2 power 2m into m factorial alpha plus 1 alpha plus 2, right, alpha plus 2 alpha plus 1 or rather alpha plus 1 alpha plus 2 up to alpha plus m. So, this is what this is called Bessel function of first kind. This is what is you get. So, conventionally you have chosen this number, okay, for C naught. So, that number will give me. So, this is how we define this. So, this is the definition. So, this is what we define. So, we will see, we will again simplify, we will simplify in the next video, we will simplify exactly. So, using why we use this gamma function, using the gamma function we can simplify this nicely, and then the definition of the Bessel function will be much simpler. So, we will see that in the next video.